So I'm Chris Knittel. I have the pleasure and honor of introducing our speaker tonight, who in many ways doesn't need an introduction, but I'll give it a shot anyway. So John has held a storied and had a storied career in both Washington, D.C. and at MIT. He's held a number of important and influential positions in both places, and he continues to be a thought leader in both places as well. In Washington, D.C., for example, he was Director of Energy Research, Deputy Secretary of Defense, and also the Director of the CIA. At MIT, he's been Dean of Science, Provost, and is currently an Institute Professor. And I'm sure he'll agree that his most prized affiliation at MIT is he's also a research affiliate at the Center for Energy and Environmental Policy Research. Just this little institute I run, or center I run. So John's going to be talking about climate change and how society should adapt to climate change. And we'll let John take it away. Thanks a lot.
Thank you, Chris. Thank you all for being here. I want to describe to you a way I've been thinking about climate change in a new way of sort of putting it together. And it has come to me, the reason I started thinking about this is after 2015 and the Paris Accord, it seemed that the system unraveled. The Paris Accord was supposed to be putting us on a path where all the countries of the world agreed at their own pace to do emission reductions, and that was over time going to get us to a point where we could avoid the dramatically bad climate impacts of increased temperature around the globe. And I noticed that at that time, there was a very large change in the way people were thinking about that, and there was an inability to continue on the path of, or thinking about of Paris, and they started thinking about the problems of doing a much greater step, instead of a step-by-step approach to climate, taking much bigger bites in reducing the climate future. So I tried to put together a simple conceptual model about how you would put together the different pieces of a much more aggressive approach to climate change. So let me begin with a, if I get these things working right, it'll be great. Yeah. The first thing that came out of the Paris Agreement almost immediately afterwards was the 2-degree target, moving the target of how much the world had to avoid letting temperature increases exceed 3 degrees from pre-industrial times. They moved the target down to 2. And there was a very influential report by the UN IPCC suggesting that 1.5 had still very bad adverse, 2 had very bad adverse, and they reduced it further to try and get to 1.5 degrees. That was a set of, which I think has generally taken hold among experts and among political leaders. Then the next thing which came out is that the original tranche of independently determined national contributions to reducing CO2 emissions, or I should say carbon emissions generally, that they realized that countries were not going to achieve that 2020 target that they had set. And they weren't going to achieve it by quite a bit. So the first tranche wasn't even going well in this new approach of Paris. And by the way, the United States is not going to achieve its target that it set for 2020. And it wouldn't achieve it if even Hillary Clinton were president. It's just something that, unfortunately, there's been economic growth and a lack of progress that one hoped one would have in clean energy technology deployments. So there was a general understanding that the 2020 targets wouldn't be met, and there became a quite widespread view, which I share, and I'll show you why, that even if you had perfect emission reductions, it wouldn't be enough to reduce the temperature increases that are going to happen out to the turn of the century and, of course, beyond. So the question is, what are the other possible general climate control mechanisms that one has other than emission reduction? So the first thing which came up is, and this was already present in the report from Paris, the present was that there was a need to worry a lot more and spend a lot more effort on human intervention in adaptation. And adaptation was actually presented in the report of Paris with quite equal weight to the importance of emission reduction. So adaptation was it was an additional attention was being placed on this as a second kind of climate control mechanism. And then there were another set of people who said, no, we're going to have to do more than that. We're going to have to take gigaton size bites of the CO2 which is in the atmosphere to help reduce the overall effect. For example, build a lot more trees that will absorb CO2 net for the world. Or secondly, to work on direct air capture, taking CO2 out of the atmosphere directly. That was a negative emission technology, has received an enormous amount of interest from the scientific community. In fact, there is an excellent report, I rarely say this, by the National Academy of Sciences, which lays out a real program for working on negative emission technologies. That is direct removal, such as direct air capture or or trees. So that was a third. And then there's always in the background the fourth climate control mechanism, which is geoengineering. That is going and putting something, let's say, on the top of the atmospheric sulfate particles, have it reduce the radiative forcing going into the globe and reducing temperature that way. So I said to myself, where is there this is the MGH. Everybody's after me. Geoengineering, which has lots and lots of governance problems from the point of view of physics and from the point of view of cost, may be yet, not yet, it is another alternative, and it may be an interesting cost-effective alternative. Now, where do I go to see how these four different mechanisms work together? Where do I go? What article do I see? What book? What faculty member? Who is active? There's got to be something I can do here, right? There's a way to shut it off, John. Yeah, there is a way. Done. Where do I go to find out where there's a conceptual framework for thinking about these four things in a properly balanced way? That's what I want to do here today. And I want to do it fairly openly and briefly. That is, if anybody has a comment or a question or something which I haven't said sufficiently clearly, let me know. There's no reason for me to proceed unless things are clear. But my main first start point is there are four different mechanisms for controlling climate. It's not right to think of them one at a time. If they work together, there's going to be a cheaper outcome for getting some level of control than if you look at them independently. The two of them, negative emission technologies, or removing CO2 from the atmosphere, and emission reductions actually work in a different way than the other two. The other two being adaptation and geoengineering. They work by putting stuff into the atmosphere, and then if the stuff in the atmosphere changes the concentration, and the concentration changes the temperature. So that is basically two physical mechanisms which are indirect because they work through the atmosphere and the CO2 concentrations in the atmosphere. abatement and geoengineering do not work through the atmosphere. They work separately, but their technology readiness is obviously a lot less than emission reduction is, where we have a long, long experience about replacing wind and solar for natural gas and coal and avoiding CO2 emissions. These other two are technologically, have a lower technology readiness, and therefore there's less knowledge about how they might work together. You see on this chart well, emission reduction means that as you reduce the rate at which you're adding CO2 into the atmosphere, the rate Q goes down. But for removal, you are actually taking the stuff out of the atmosphere. We haven't done that yet. So if we started doing removal of CO2 from the atmosphere by one technology or the other, we'd be starting somewhere between the year 2020 and 2100. And we would try and get to a point eventually where there's net zero between these emissions and the removal. OK, here's the model. It's all there is. It's the only place that will need some explanation. The first thing is when you look at the climate damage, which is done, the damage which is done by climate change, what that does is it creates a loss of GDP. And the normal way that that's expressed, I believe I'm saying this correctly, by economists is working with a damage function. And that damage function relates the global increase in temperature, delta T, to the loss in GDP, whatever it may be. Now, I am of the view that nobody knows what that damage function is. Several have been put forward. We have one in the so-called model from Yale, from Bob Nordhaus. We have one from Marty Weitzman, which is an exponential, but nobody has any independent or empirical or experimental way of telling you what the shape of that damage function is. Fortunately, today, we're going to stay at the level of low damage, and everybody agrees that in the state of low damage, there's a proportionality between damage and temperature squared. So that is illustrated by the second slide. And I've taken the expression which has the temperature change squared, and I've now put in the 4 different physical ways that are available to lower that damage. The first one I'll point to on the left is here illustrated by the variable chi, I hope, chi, which refers to abatement. And there the idea of abatement is you are reducing damage regardless of what the temperature is, because you've spent the money, for example, to buy dikes all around Miami or other places, or put in trees, that they will always be taking out the CO2 and reducing damage, but they do not work through changing the temperature. Global geoengineering now has a squared effect. Its variable here being denoted by lambda. It has a squared effect on reducing. Why? Because if you put it on the surface of the globe, everybody gets less radiation forcing. The radiation forcing drives all the temperature down. And so it is a squared effect. And the other two, the emission reduction, denoted here by the variable phi, or the CO2 removal, act through the temperature by, first of all, influencing the concentration in the atmosphere. So we have to go one step further to understand how the temperature responds to changes in either the emission reduction or in the CO2 removal to get a overall effect of how these 4 different abatement mechanisms work together. And that's the heart of the approach that I'm proposing to you, because it is advantageous if you could actually mount it in a practical way. Ignoring it isn't good. You can ignore it and say, well, we don't know how to measure these things, which is true, but we don't know how to measure the damage function either. So we have to really think a little bit about how we're going to handle this. But in this particular case, we have a situation, the way I've structured this is, if you have no abatement, chi is 0. If you have completely successful abatement, chi will be 1, and that's true for all these variables. So these variables, each one of them is intended to show how the independent physical control mechanism can have an effect on the overall temperature. Is it clear? Is it unclear? Or is it boring? Yes, sir.
Your function seems to have the same major defect in it that Nordhaus's did, which is there's no steps in it.
I'm sorry, there's no what?
No possibility of a step function.
There surely is a possibility.
Otherwise known as a tipping point.
Yeah, there is. Both of those remarks are absolutely correct. The tipping point would have to occur through some mechanism which I'm in the damage function itself. That is, the damage function is not continuous necessarily. It could just pop right up at some point. And that's certainly, in this, the method here would apply to that. That is, the approach that I'm saying would work for being close to a tipping point or far away from a tipping point. We don't know that they're tipping points, right? But if we're near a tipping point, all 4 of these control mechanisms are in play. Oh, so we have to figure out how the CO2 emissions are influencing the temperature. And I take the absolutely simplest case I can to keep matters simple here. And that is, we got to go from the emission rate, which is here denoted Q of T. It goes and influences and changes the concentration in the atmosphere, C of T. And then that goes and changes the temperature, capital T here. So I do this in 2 steps. The first step, I wish I knew how to work this thing. Yes?
I'm glad to. What, you want a point?
I want a point.
All right, let's do it. There's that little red button right there.
You criticizing me?
Not at all.
Okay.
Of course.
I think he did that, not me. Aha. So here's the concentration in case we had none of the 4 climate control mechanisms working. Here's how the concentration would change in the atmosphere. Concentration at time t is the concentration at some arbitrary time 0 times the time integral of the emission between those 2 times. 0 subscript on the concentration says no climate control mechanisms are working. Now, if we have both emission reduction and emission removal working, the resulting equation has this form. And you can see in this form here that if this is non-zero, there will be an emission reduction term, which changes with time. And this term here says if I'm taking stuff out of the atmosphere, I'm doing it, I assume, proportionately in time with the initial concentration at the initial time of this work. And from that, there's an equilibrium sensitivity relationship. I get this following relationship down here, which produces an equation for the damage now in the presence of 4 different control mechanisms working at the same time. adaptation, geoengineering, emission reduction, and emission removal. That's the model. Tell me another model which tries to put all 4 of the mechanisms together, even as crudely as this one does. Okay. Oh, yes?
So is the damage at a particular time or integrated over some time?
If you're a fancy economist, there's somewhere in the audience, you would discount it. But then all I have to do is put an extra exponential in here with a discount factor that somebody will tell me and integrate it between the 2 time intervals I'm looking at. I'm not going to do that. There's also a bracket here, an angular bracket, which reflects the fact that indeed there can be stochastic activity, one which brings you to a tipping point or not. And so in this formula in this case, the damage at a certain horizon time, h, there's an angular bracket there which takes into account that there may be a lot of stochastic behavior in the flow of emissions, Q of t. I'm going to give you one simple example of that at the end. But let me tell you, it is important. That's the model. And what we're going to do is we're going to use it, apply it to a couple of different places, starting with an initial time, and then going to a final time. And if I'm right, since I want to minimize the costs of the damage, I want to minimize damage, I have to take a budget and say, how is the best way to spend that budget so as to get the lowest possible damage? For that, I need a cost function. I need a cost function for each one of these different climate mechanisms. Nobody on the globe knows any of those cost functions. And I'm no different, I know. But then that shouldn't stop me altogether for 2 reasons. The first reason is nobody knows anything about the damage function, but they proceed anyway. And the second reason is, even if you don't know the damage, the particular cost function, what you do know is that the linkage is there as described in the damage expression for the model on the previous slide. So I have to do something about the costs. And I just want to do something about the, again, I stress to you, you could say to me, I don't want to hear anything more. If you don't know anything about the costs, you can't really do the optimization. That's true. But I don't know anything about the damage function. I still do the optimization. That's what the integrated assessment models do. So what I'm going to do is I'm going to say, let's just illustrate what can happen. Let's just illustrate how much it matters to take the linkage into account. So the idea here is to say, and what I want to do is I want to find an enterprising young person to help me build a tool on the web which lets anybody evaluate their set of cost functions that they might want to look at. So I'm not advertising my cost functions as anything more than something that I've picked out of the air in order to illustrate the importance of taking into account the linkage between all 4 of the climate control mechanisms. And so what I do is, to make it as simple as possible, is I say all of the cost functions, which are here for the 4 different abatement schemes, will have the same functional form, and they will only differ by a scale factor here. And since I'm going to say something which is not true. Since I'm an honest man, I'm going to look at 2 different cost functions. One which increases with scale, increases with a variable, and the other which decreases. So I take the simplest case, this one which increases with scale, high cost, and a low cost one which goes to a constant factor as you increase the variable. So those are the 2 illustrations. And now look at the numbers that I take. I have a communications consultant who advised me on these numbers. None of them have any reality. But look at them. One of them is $50 trillion. One of them is $100 trillion. And two of them are $150 trillion. Now remember, that's being spent over 80 years between 2020 and 2100. So it's really not, for a guy who's worked at the Pentagon, it's not a lot of money. Remember the, sorry?
U.S. only or world?
World. I don't deal, world.
Right.
Now you could say to me, there's another issue which is not being addressed in this seminar. Is the world going to be able to work together, much less the United States, on this problem? But that's not. I want to fix people's mind on a framework that recognizes that you've got to look at all three of these methods at the same time. So it's $50 trillion for, and I actually have a reason for choosing these numbers, but any of them will give you a similar result, not a similar numerical result, but a similar result of how important the coupling is. So we're going to take this as the cost with those numbers. I now make my life even simpler by saying the rate of emissions is constant. It's 2 parts per million of CO2 per year added to the whole globe each year into the atmosphere. Not emitted, but into the atmosphere. It's about half of what's emitted goes into the atmosphere. And it's going to be flat. And by the way, if you say to me, is that a reasonable number? Let me tell you, that is dead on to what's been happening. About 2 parts per million per year. And I then go and I go here and I look at now this linear approximation, that is, concentration is linearly increasing before I add the 4 mechanisms. And I say, now this is the damage function for that simple linear case where there's no variation in the flow rate. It's always 2 parts per million per year, and there certainly is no stochastic behavior, and there certainly is no tipping point. But if I was younger, which is unlikely, and smarter, which is hardly possible, I'd be able to do this for a discontinuous flow rate. And I now just give you the results. Here's the Paris goal originally in 2020, or 2015. And here's where they want to get to. And here's how much it's going to cost to optimally make that reduction in the 2100 temperature go to 2 degrees. Somebody has come here and changed this from 2020 to 2100. That's what it's supposed to be 2100. It's $3.9 trillion over the 80 years for the low-cost case, and it's $8 trillion over the high-cost case. Well, now what if we go to a deeper goal? We go to a deeper goal that is the 1.5 degrees in 2100, which is what people are now urging. Of course, it's a deeper goal. You're going to have to spend more money for more of these 4 mechanisms to be working together. And in that case, the numbers jump from 7.3 trillion to 17 trillion. Yes, sir?
So I think I'm confused about what you're saying here. So it sounds like you're saying this is the cost of going from the 3-degree goal to the 2-degree goal.
Correct.
So you're presuming that the cost of getting the 3-degree goal itself is 0 or understood or not part of the calculation somehow?
No, the cost of the 3-degree goal is in the calculation. It says we know where we're starting, about 1 degree. And if all the chi and all that was, the one thing which would be remaining there is delta T of T0. That's the temperature at 2020. And then the next piece there would still be there. The only thing would be there would be the AQ term, if there was nothing. So there's a base of the cost of doing nothing.
So if I just want to hit 3 degrees, do I get the cost of doing that out of this somehow? Or is that
That's what you get. That's what you get, yes. That's exactly what this number is supposed to be if it was properly labeled there, 2100. That's how much it costs to get the world from what it expected was going to be right, 3 degrees, to what is its now new target in 2100. I'm sorry, what it was expected to be the correct 2100 target of 3 degrees. To go to
I'm starting with business as usual as the current model, and then cutting that down to 3 and then 2 or something. But that's
well, I mean, business as usual. I told you we're doing it at 2 ppm per year. That's what we're doing at business as usual. I consider today business as usual. People may think it's not business as usual, but they're kidding themselves.
And in your model, that would get us to 3 degrees?
That's correct.
Yeah, so that 3 degrees is business.
And I've mislabeled it so it doesn't help you, huh? Right. But look, what happens if we're wrong? And we're really going to 4 degrees. By the way, in my heart, I think we're going to 5. I mean, more. I mean, people don't talk to me. I'm so pessimistic about where we're going as a country, as a globe. So if you go to 4, now you see the numbers really begin to, get a little bit higher. And that's where the stochastic part comes in, even not worrying about the more dramatic issue of tipping point. If you were doing an integrated assessment model, that would be an important deal. And why do I care about that? Because if I'm working on emission only, I want to make sure that I have the most cost-effective emission program. I'm very sorry about these. Now, this is a complicated slide, but I want to do it for one reason only. Same on the top is the same, should be the same number for the low budget case and for the high budget case, for going from 3 degrees to 2 degrees. But here is what I want to, and here I actually show you the budget shares for all the different 4 mechanisms. See how they differ? And how much money they take up of the 3.91 billion. But what is more important is if we used individual separately, each one of the 4 mechanisms separately, and say, we're only going to do emissions. Then to get to these totals, instead of being 3 or 4, it would have to be 8.9, 8.8 for emission reduction. So you basically cut the costs in half by spreading it out between the 4 alternatives. Now, if you go and look at these integrated assessment models, I never see any of that. They may have it buried in their assumptions, whether they use backstop technology or some other fancy stuff. But it's only presented as an emission, a change in the amount of stuff which is being put in the atmosphere. Similarly, the same story for the high cost. There it's even more impressive. If you try and do it with emission in the high cost, it's going to be $336 trillion because that curve is going up there like that. So this is supposed to be a vivid example of how much you save by optimizing between 4 different cost components. It's a vector. It's not a single quantity. And you could say to me, John, all of this depends upon your assumptions about the costs. And the answer is no, it's not. The particular numbers are going to depend upon the cost, the cost. And it may be that it won't be a factor of 2. It may be a factor of 6, or it may be a factor of 1/6. But the linkages are there. And here, because I did it for all different budget sizes, I show you how, as the budget changes, first of all, how the damage goes down. There's, of course, a big difference. This scale is, This scale goes to 15 billion for the low case, and for the high case, it goes to 100 to bring the damages down. And this is how the control mechanisms, fractional shares change over that large change in budget. And these are all, I remind you, trillions. I should say to you, I went to the library and I discovered that the global GDP is about $90 trillion per year. So that's how it looks. Again, because I don't have stochastic behavior in here, I don't have a time-dependent emissions, I don't have any discrete or bent control shares. Okay. Also, this chart, you don't have to look at it. I just want to make one point. If Q increases, that is, I go from a constant 2 parts per million per year to 4 or 6, or I go to 1, I'm going to get a slightly different number for the cost. I'm sorry, in this particular case, I did it for fixed costs, so it shows you the change in the shares. But you can do it for anything you want. The point is, I did it for 2. You could easily do it for something else. Aha. There's something called the social cost of carbon. What is the social cost of carbon? The social cost of carbon says if you add 1 more kilogram of CO2 to the atmosphere, how much do you increase the damage? Is that right? That's the social cost of carbon. So here, I've got, whoa, I can calculate the social cost of carbon. It's the partial derivative of the damages with respect to how much stuff I add, Q. But I now have the additional problem that at any particular point, it depends upon how much of the climate control of the other variables, what their values are. It is, in fact, a partial derivative now with respect to the 3 other. And so when I do that, and again I see that the low cost, when I use the low cost numbers, this is, social cost of carbon at 2 ppms is 1.71 as a ratio to 2.92 if there was no emission, if there was no control mechanisms operating at all. So it's, I mean, it's roughly a half. And the high cost, what is interesting, trivially interesting numerically, is that it's actually a lower ratio than when you use the low cost, the change in the social cost of carbon. I remind you that I've been using parts per million, but you want me to use per kilogram of CO2, so I'd have to divide by this factor to make those numbers come out in the same set of units.
Question about the units?
Yeah.
So if I want to set a carbon price, do these numbers tell me what the price should be in this model?
If you had a more talented and more careful lecturer, he would tell you that in this particular case it was $6.
$6.
Yeah. But if you want me to get another number, all I have to do is go back and fiddle my, yeah. So I mean, you shouldn't trust any of these particular numbers. But you can absolutely, yeah, and this, absolutely. Now, why you need this number is another question. You need this number for regulatory purposes. If you want to set a carbon price, you have to tie it to something. But if you want to set a carbon price without looking at any of the other 3 different, I should have said something else. If you only had, because I know there are plenty of people in this room who are not willing to take on geoengineering now. And we only had 3, adaptation, taking CO2 out of the atmosphere, or reducing emissions, you'd still get a tremendous benefit. So you don't have to buy on to geoengineering. I claim that we will be buying on to geoengineering sometime in the future. But the point is, 4 is better than 3, 3 is better than 2, but it's not 1. This is my pathetic effort, sir, to begin to address the issue about a tipping point. And for that, I have to be able to solve this optimization problem. This is why I'm scared of coming to your class. For variable change in the emission rate over time. So I have to be able to solve the original. I'm going to go all the way back. This is the problem I really want to solve with a variable Q of t. If I have a variable Q of t, let's say 80, because I'm looking at the years 20, because I want to be policy relevant, I'm not going to be here in the year 2100. Others may be, but not me. So if you have 80 years, then you'd have to have 80 time bins. And in each time bin, you'd have to have a different coefficient that you're solving for the optimum amount. So you'd have now 80 of all 4 of those variables chi. And that's beyond me. Those are my main points in this effort. Yes, ma'am.
So when you're looking at costs, the cost also include the cost of developing these technologies or simply implementing technologies that somehow magically finance?
They're really two separate. Firstly, the answer is this is not sufficiently fine-grained to make a difference between development, deployment, first of a kind, nth of a kind. This is costs and the way is carelessly used by economists. Okay.
But I just want to remind you, ITER, 20 billion. So
This is trillion.
yeah,
Trillion.
So billion becomes pocket change.
It's always the way it's been for me. You made me lose. I wanted to say something else about what you just asked about development. The cost here, I'm now going to really get myself in trouble, is a little bit more about how much would you be willing to pay. The only thing there which is uncertain is the capstone value, the scale. I said it was 50, 100, 150, 150. That's where that cost is not really a cost in an engineering sense. I think the way you should think about that is a willingness to pay. How much would be you willing to pay to get rid of all, let's say, of the emissions? How much would you be willing to pay to get all the CO2 out of the atmosphere? Now, how you do that in an engineering sense, not here. But it's a framework that I claim the framework exists. The numbers don't. Yes, sir.
So in this model, what happens to cost after 2100? Like, is it going to stabilize or keep going? Or what happens after that?
Well, first of all, it's of minor interest to me, since I won't be here. But the point, there's none of this work. Nobody. I mean, there are people. I mean, they're like all of his slides and his charts go out to 3,000 years, right? I mean, whatever it is. But all of the policy discussion leaves you at a cliff at 2100. I don't celebrate that, but I mean, I just did that because that's the relevant policy discussion. But of course, you have to keep on doing something. No, him, please.
So I was wondering, so geoengineering and adaptation could potentially be highly localized, whereas sort of the emissions reduction.
Geoengineering is not going to be highly localized, and adaptation probably will be highly motor. I point out that we don't have very good policy tools for doing human and so you're going to let Miami do it itself and so forth. So yes for adaptation, no for geoengineering, but these numbers assume a single actor for the whole globe. Yes, sir.
I don't think that the right way to handle tipping points is by taking an average of an expectation value of the damage function, because once the tipping point is passed, essentially we're headed for 5 to 10 degrees. It doesn't matter how much money we spend after that. We might as well set it to infinity at that point. And the right way to deal with that problem is to model it by modeling risk. And people, you want to say willingness to pay, willingness to avoid risk. We all take some level of risk. We drive cars even though we have a chance of dying. So there are ways to do that.
Correct.
And that's really the right way.
You're absolutely right. You're absolutely right. But I want to say that I didn't tell you what my probability density function was. And it had some big discontinuities in it. But you're completely right about what you say. Yes, ma'am.
Did your results indicate a breakdown in which types of negative emissions technologies?
Certainly did not. And by the way, it's an open, you see, I said to you at the beginning, technology readiness is not there with either negative emission technologies or with certainly geoengineering. I will tell you my own view is that it's going to have to be largely, I don't want to tell you my own view. I don't want to tell you. Yes?
So, thank you for the talk. I'm an electrical engineering by training, so I want to dissect what you presented from what I understand, and also want to hear from your comment. So fundamentally, your problem is about the optimization. And that optimization, if we all take the optimization 101, if it's a convex optimization, then your best bet would be to exhaust one of the solutions, right? In a convex setting. But your conclusion suggests that don't put eggs in one basket, put them into 4 baskets. And I think the fundamental reason is because the model is a non-convex setup.
Why do you say that?
Like if you have a linear programming, you have 4 decision variables, then you will always want to max out the one that...
But it's not a linear program.
That's what I'm saying, is that because fundamentally the model, I'm trying to dissect that. The core policy recommendation come from that modeling of such a non-convex problem.
It's convex. It's just non-linearly coupled.
That's right.
It's convex.
And that's sort of a, and then of course we can debate about the fine detail about how much of each percentage, but fundamentally that's sort of the reason that why you have such a policy conclusion that you really have to put 4 different things together.
Are you agreeing with me or not? Stick on that point. Stress that point. I'm sorry. Yeah. Paul. Yeah, I'm sorry. Yes. Go ahead.
I'm trying to get basics here. Your definition of damage function and cost function are confusing me. Can you just define what the differences are?
The damage function is what happens to the society when temperature goes up. And its units are percent of GDP or fraction of GDP per temperature increase squared. Okay? And that's the common definition of damage function, I believe. Paul.
It's not clear to me why you couldn't possibly get a solution with 1, 2, 3, or 4 instruments, depending on what you assume about the level and shapes.
I'm absolutely certain it's true. I mean, it is absolutely true. I didn't find it. I mean, I was amazed. I used Mathematica. I was amazed that when I punched the button, how quickly it came out with these numbers. A lot quicker than I could do. But you're completely right. I do not rule out here any corner solutions.
But then you have to make some very strong assumptions about the level and shape of the cost function.
Since I don't know anything about the shape function, or does anybody else? Yes, sir.
Professor, when we say about the emission reduction, we are seeing the vehicles, for example, zero emission in EVs, but you use energy from coke, burn coke, for example. What do you think about the evaluation of life cycle as a scale for this?
I haven't gotten into biodiversity effects or life cycle effects or this or anything like that, but I don't really quite know where you want me to go on that question. What would you want me to say? I'm happy to give you an answer, but I don't know what you want.
As you know, I know nothing about these things, but I'm going to still challenge you a little on the mathematics. I mean, the qualitative conclusions that you have reached would have been reached with
any function that coupled these things together. I don't think those special form of 1 minus chi and all this is what's doing this. Any coupling between all these variables will give you every one of your qualitative reasons.
So, Arup, let me say something to you. I don't know which part you object to, the 1 minus chi, or you mean the function, or the cost function?
I don't object to anything. I'm just saying you could have chosen any function that would couple
No, but what?
together and you would have found the same law.
I'm sorry. The heart of the problem is that these are coupled together. That's my. I think you may have to. They may say everybody says that and knows that, but I don't think so. But it is, in fact, what you say. It is that is the heart of the problem. I chose the specific architecture of 1 minus chi because I wanted to say we're in the business of trying to solve the global climate problem. And that means you got to get rid of the whole set of these things eventually. So you have to, and that's why $150 billion, $150 trillion will do it for you. Yes, ma'am.
So your results were sort of showing the amount we should spend in each of these 4 different areas.
The ratio.
Yeah, but do you also look at the time frame over which those funds should be spent? Because surely with emission reduction, those investments should occur earlier.
It depends who is the director of energy research.
Okay. Because several of these technologies still have, a period to develop before they.
And that's, I also said that the technology readiness of 2 of them are really completely in the box. But I will tell you one thing which is interesting. Carbon capture and sequestration, which I guess is what you're doing for us, that is actually key because it appears in more than one place. So if you could get me in my life, even after my lifetime, an economical carbon capture and sequestration with good governance, that would make a huge difference in several of these different control mechanisms. Yes, sir.
Yes, your bottom point about avoiding overspending on emission reduction.
I know, that's terrible, isn't it?
Yes, it is. At what marginal cost do you consider that we're overspending?
Well, in order to give you a good answer to that, I should have said not overspending, but overthinking emission reduction. That's what I should say. That's all we talk about. That's all you talk about. In the world I live in, that's all people talk about. But you're quite right. It would be a marginal calculation. And since I don't have any confidence in the numbers I've used here, I don't really want to throw it out as a possibility. But I'm saying to you, everybody talks about emission reduction. That's what I'm saying, yeah. Yes?
So supposing all the formulas were known, the constants were known and everything, is this approach one that could only be implemented with a planned economy, or are there some market mechanisms that could get you to the, for example, in particular between emissions reduction and removal?
If it was a planned economy, I'd have to do the planning. But other than that, the answer is, it's really basically saying that you're dealing with the economic idea of minimizing costs for the society. I think that's pretty good. If you tell me practically, we're not anywhere close to that. But that's why we're so far away from making progress on this problem. Thank you all very much. Thank you.